Okay, welcome everybody. Right, so this is going to be a session on theory of computing. Right. Okay. Why I thought I want to do this is basically after releasing of this LLMs, the generative AI space and everything, people really get confused when LLMs takes really a lot of computing space and all that. But what exactly is the computing? I mean, like, what does computer has to compute at that level, right? Yeah, obviously there would be computer algorithms which has to be get computed, more or less, all the models which we write on everyday basis and all that. So in these next couple of sessions we'll be pretty much talking about capabilities and limitations of computers, right? So it is pretty much a vital and very interesting topic moving down forward the road. So uh, we will be pretty much learning the computability theory. Okay, this particular field, right, it got explored in almost all 1930s and 1950s. I mean, like, you know what is computable? Okay, we'll learn about that. Okay, and then examples in that and models of computation and all that, such as finite automaton and Turing machines and all that, right? And you know when we really have to compute something, right? So it need to have some sort of a mathematical truth to it. I mean, that's what we say, logic when we do program or anything, right? And yeah, and it should have some level of program verification. I mean, whatever the program which you are doing, right, it should pretty much lies on those verification principles and all that by having the mathematical truth. Okay, so that's what we'll learn. But there is a lot of research which happened in this area for the computability theory. Okay, now I'll share the links if uh, there are plenty of them. I'll share the resources in the in the description section of this particular video and all that, right? Okay, and then what a person really can expect out of this, right? As you know the computability, or as the computing is happening, right? you know what are the different kind of practices does we have to do while tokenizing, while factorizing, while embedding and all that? What are those kind of computabilities which we have to consider? And all this can be kept in one particular theory of complex theories. We call it complexity theories, right? Right, and this is being still researched till today. Okay, from almost till 1960s, complexity theories, right? So after a person has figured it out, this is what I can compute, and this is what I can break into the chunks, this is what I can pretty much do it, right? Then this is where it went out, right? Such as P versus NP problem, measuring the complexity, I mean, like time space, probabilistic models, and interactive computation models. And recently, if you guys heard about this, right, Google came out with Genie. It's another kind of a model which is going to get released. I mean, like, it's up in the market. You can search. Yeah, uh, right. So, yeah. So the pretty much the prerequisites to understand this, you would really need some level of mathematical concepts, theorem, and proofs where you can understand, right? And what is a theory of computer science, basically, where you can pretty much do this, and we'll see the applicability part, basic research, and connections to the other fields, and also we'll see what is the nature of computation, right? So as I told in the starting, let's begin with something else, a simple thing called finite automaton. Okay, what is finite automata, right? So finite automata is a computability theory, okay, which helps in optimizing, in computation or anything, right? So let's consider M1 as a model, right? So this model and Q, this is the model, and Q's are the states, okay, right? And whatever you're, and there's, you know, a circle. I mean, like I didn't draw the good circle, but yeah, this circle. You can say this circle as a state, okay, and then a circle with the double, and this you can say accepted state, right? Okay, so let's say when does, you know uh, any model can be accepted, okay. Uh, any idea? I mean, like, when does any model can get accepted? I mean, like, when you're embedding something, right? When you're embedding that particular data, when you're tokenizing something, okay, when does this model really gets accepted? I mean, that particular model which you're writing in a finite string. Hope I don't have to give you the, lecture or small things on NLP, the basic NLP, right? So when does it really happens, right? When does a model really should accept? I mean, like, whatever the chatbot which you're developing, when does it has to pretty much give the user that kind of an output, right? And one more notation which I forgot is, when I say one, it's an, it's all about, at the end of the day, it's all about what ones and zeros, right? That is what it is, right? Basically, okay. I mean, all the string, all the, natural strings or anything, we'll just convert them ones and zeros, and that's how the machine learns, and that is what machine at the end of the day computes, right? Basically, right? So this is nothing but the transition state we call, okay. Cool, fine. So let's take a finite automaton problem, okay. For example, let's say, 0 double 1 1 0 1. This is an acceptance state, okay. We are saying this is what you have to accept, and 0 0 1 0 1, and this is what you have to reject to a model, to a system, okay. And you know and what is that, why I'm considering these two, you might have been curious, right? So I'm telling to the system, okay, to the model, whenever you are going to get, okay, two consecutive numbers, right? Hmm? So please accept them, you know please accept them is what I'm telling them, right? So anything, okay. So this particular acceptance and rejecting, this is the first level, okay. Whenever you get two consecutive ones, such as you can just see over here, that is what I'm telling. And if you don't have them, then just please reject it, okay. So yeah, I'm just going back to make this pretty much look neat, right? So let's say, let's have this model, right? Transition and Q1, right? So Q is a kind of a start state, right? Q1 is the starting state. You have three different kind of states over Q1, Q2, and Q3 is where you are starting, right? So now I I want to get this string out, right? 0 1 1 0 1, which a system is eventually accepts, right? So it goes 0, okay, and it has to get transition from one state to another state, right? 1, okay, these are the states, fine. And from here again it goes to the 1, right? And let's see, and it gets accepted, right, in this state, Q3 state, right? And let's see how does a system really rejects. It doesn't go to the end state, right? And yeah, and the system, it got accepted, and it has to send back you some sort of an, what do you call, acknowledgement loop, whatever, right? It has to respond you back. You have sent out the entire string, whatever you're asking, you have sent out, and the model should really accept that condition, right? So Yeah, my bad. So you have 0 and again and 1 basically, right? The string gets accepted, right? For example, let's take the same thing, okay? Let's take the same thing, 0 0 1 0 0, right? So you have the same notation of 0, and again it goes to 0, and from here you get to the transition of 1, and again you know you have this 0 and again 1, so it is not going over there, right? Yeah, done. So let's say that A is a language, okay? A is a language, some language, right? Whatever that language of model M1. So what happens when M1 recognizes A, okay? This is A. So what happens? A is equal to L of M1, right? Simple. So as M1 is accepting that language, right? Is you know M1 is accepting that language, right? So what we can say that A is equal to W is nothing but some notation where I'm saying W is bunch of words what we have in a string, okay? And this W contains a substring 1 1, as we spoke, that that particular that particular string has to contain some consecutive 2 1s, and that is when we are going to act. And this is what when you pass through that M1, okay, so it gets accepted. Otherwise the other conditions whatever you have, it will not get accepted, right? So this is a basic level of understanding finite automata. I mean, you cannot literally send any kind of language whatever you want, and that's why if you see more often, what happens, everybody try to teach any kind of model, any breakthrough, right, in the English language first, right? Because that's international, widely recognized, and that's what we program also every day, right? So just remember these two, okay? A, where W contains the substring of 1 and a 1, consecutive ones, and that's how the finite automaton pretty much accepts that particular kind of a string, and why it doesn't accept the another string. All right, so let's say if you have you know where a finite automaton M, okay, is a you know a phi tuple, right, which has Q, summation, which has this delta, and Q0 as the initial state and F as the final state, right? And set of acceptant state, the final state, right? So what happens over here, Q is nothing but finite set of stages, right? States, right? And sigma is nothing but finite set of alpha symbols. I'm just alphabet, as I told English, right? The symbols, alpha symbols, right? Yeah, all these you say A, B, C, D, all these are nothing but we have gave them the sound and everything, but these are some sort of a notation in the language where we use, right? So we call them alphabetical symbols, right? So that is sigma, right? And then the transition function, which is nothing but the delta, okay? So it has to get transition. You have the plain PDFs which are dumped out right over here, and then you need to pretty much transition them into some sort of an embeddings, right? And then vectorize them and all that. So there is huge number of and the model really have to accept. Again, just think this as a foundation moving down the road for next couple of the minutes, what we are going to discuss pretty much, right? The transition function, we call it, right? transition function, right? Delta, right? So what is this transition function? As you have seen, okay, so in the previous example what we discussed, you know a is equal to L of m1, where a has w and contains 1 1, right? Cool. So now how this transition function works, right? So the delta factor, the delta, my bad, I'm sorry, just ignore all these. Okay, yeah. So the delta is nothing but you know q times, like the cross function, the cross product, which gives you the q. So every time it goes to another state, right? It's a finite set of states which we have, okay, right? So this delta is nothing but whenever you are putting that in a finite set of alphabets together, okay. So the same thing what we discussed, right? So it has to go and land at some state basically. So the delta transition function would be the same. And for example, let's say q and a are two different things, right? Q is the state and a is an alphabet, which is nothing but r, which comes. That means what it happens is, from q state, okay, to get to the r, which is an accepted, and a, okay, will essentially become an r in an accepted state in the final state, right? And q0 is nothing but, again, as I told you, start state, and f is nothing but set of accepted states, right? Cool. So for this, I'm going to just give you the same example of getting those two ones and negative ones. For example, let's take m1, right? And you have this, and q, it just got started, as you can recall it, 0, right? And q2 and q3. So it goes here, which is 1, and then 0, and then 1. Like the other one, this is 1, 0, 1, right? So over here, if you just see, m1 would become q sigma, okay, delta q1 and f, right? My bad, right? And the q, which are the finite set of states, that are q1, q2, and q3. You should know how many numbers. This is a finite set of states. Let's say if you have, when you're building an bigger neural network, you might have a question. How can I pretty much answer the question for an infinite kind of set of states, right? But as I told you, that is nothing but a complex theoretical problem which has to be solved, and a lot of research which is going on, and there are definitely solutions for that, okay. It's not something, okay. And the string, the alpha, would be 0 comma 1, right? And the finite last is nothing but q3, right? That is the accepted state, right? So over here, if you just see the delta, okay, so 0 and 1, right? q1, q1, q2, q2, q1, q3, 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 and q3. And if you just see, this is a simple table which I'm just giving to you, as you can just take the notes basically while you are seeing this video, right? So hope you understood the finite automaton, okay, as the formal definition what it is, right? So please remember these notations, right? I mean, like this would be the Q0 over here, right? But this is for a model. This is the phi tuplet kind of a problem, right? Okay, cool. Let's move to the next. Okay, the computation of the finite automaton. Okay, string and the languages, right? A string is a finite sequence of symbols in pretty much sigmoid function, right? A language is a set of strings, right? Cool. So that is the string and language. Okay, and then what is an empty string? Okay, empty string is the uh, the epsilon value basically. Okay, we'll call it an epsilon value, right? So is the length which has the 0. This is the empty string, right? What is an empty language, right? So similarly, I mean, like sometimes you'll be seeing this, the last strings or the last missing values, right? It's nothing but the 0 cut it into half, right? But yeah, is a set with no strings, obviously, right? That is the difference between a string and a language over here, right? So let's say if we have to recognize a language, okay, where you know uh, yeah, where L of M is equal to W of M accepts W. So that's what we thought, right? Which is nothing but A, if you just see in another sense, right? Cool. And let's say L of M is nothing but is the language of model M, right? Is the language of model M, right? Where M recognizes the language, where M recognizes the language, right? Good. So let's get into the definition of M, accepting the strings, right? So let's say, M, accepting the strings. Hope you guys know what is a string. String is nothing but the finite sequence of symbols of sigmoid function, right? So a language is a set of strings which might be finite and infinite, right? But the string is a finite sequence, as you know, right? Let's say M is accepting a string, right? So where W is equal to W1, W2, comma, and keeps going on till Wn. Okay, so let's say Wi belongs to sigma m, sigma function. If there is a sequence of states, okay, in the past state what you have seen, q which gets transitioned from q state which goes to the final state of r. So let's say there are sequence of states which are r0 which starts with q0, nothing but, right, and r1, r2, and keeps going on till n, right, which all these pretty much belongs to the finite set of states, which is nothing but the q, as you guys can remember. Cool, right? So now what happens is where r naught, which is r0, and q0 is equal to, and when you see ri, okay, right, what would be an ri? I mean, like wi, for that particular wi, what would be an final state? I mean, like what would be the final state, right? So that would be the delta of ri minus 1 comma wi, okay, for where it should pretty much behave between 1 the I and between the n, right, the nth, right? Okay, so that's when the Rn would pretty much belong to F, the final set of state, right, where again where M is accepting the string, right? Okay, and then moving out, saying that a language is regular if some finite automaton pretty much recognize it. Let's say if it is not recognizing, then it's not an irregular language, right? So we are conditioning that language. For example, let's say you have to read the PDF documents, you have to read the tabular data, you have to read the image data, you have to do this, right? It's all these falls under this regular language processing, the RLP. I'll just put this in a different, right, in a different color so that you guys can feel it and do little bit of search about RLP. My bad. Okay, RLP. So till now you guys might have heard about natural language processing, but there is another thing called regular language processing. So is the computer capable of computing that regular language processing is first what you have to learn, and then you have to go to the natural language processing. Okay, in another sense, right? So because this finite automaton, for example, this is an algorithm, right? So can it really do that? That's a kind of a computational model, right? The finite automata, can it really do it? So whatever the computation model which you're choosing, you should pretty much behave in this way. Okay, at the end it should pretty much behave in this way, and it should pretty much do that computability on the complex problems. So you have to select the wise kind of models, right? So that's why you try it on the regular languages first and then move to the natural language. It's not like directly you are hitting that 100 step. To learn this computability theory takes really good amount of knowledge you should really have on that, right? Okay, so yeah, we'll move to the next part anyway. Applying this finite automaton on the regular languages. Till now we have seen the computation, the definition, the formal definition, and then a quick example when we started, right, and all that. So go to the regular languages, right? So let's take the same example, right? The regular, irregular, and all that. So you know for example, let's say when we are telling L of m1, there's nothing but a in another sense, but it's fine, right? Where a is in what is a? Basically, it's a regular language. It's a language where M1 can recognize, right? So we are just telling that, right? So when we are going deeper, therefore a is regular, right? So therefore we can say a is regular. Okay. So it's regular. It's not new. It's because it got trained on that particular thing. It got know what that does that data contain and all that, right? So it is pretty much regular for it. That's why when you go and ask any kind of thing for chat GPT or any application, so it gives you regularly, and that's why people keep on telling that you need really good prompt engineering to get the good answers, right? So that is what varies basically. Prompt engineering is more of engineering the understanding the languages basically. Okay, where to apply what kind of language. Is it a regular, is it a natural, is it syntax based, is it tokenized based, and all that you need to really understand. Okay, and there is a very good thing I was reading about one of the author while I have to do some sort of research on the ambiguity and all that. I'll put that in the link anyway, right? So it's really classifies about how does the ambiguities comes, difference between. It was almost all this research has been done in 1970s something, right? So yeah, we are telling that one now the language model M1, I mean the model which recognizes the language, therefore a regular language M1 which contains substrings of you know ones, so it is regular. Okay, right? Things of one, right? So it's nothing but hey, cool, cool. So similarly, let's take more example. Let's say B. right? It's a kind of a language, okay, which has, the words, the strings, has only the even numbers, okay, numbers of ones, okay. And let's say, C. Similarly, you can just, these are nothing but guard railing the system and doing that. So this makes a regular language for practice, for the finite automata. Let's say, has only, you know, odd numbers of ones, okay. Or else you can even do another thing, right? uh, let's say the strings which you have, I mean like W, which has which respects, which is you know factors of 3, right? Similarly, you can, all these are kind of regular language. For example, you know we cannot just say, for example, let's say, E, okay, which is W, and W has, equal number of zeros and ones, okay. And this cannot be a regular language, okay, because zeros and ones cannot pretty much be on the same page. You understand? The regular is something which is pretty much drafted out in a nice way. I mean, like in a very clean way, saying that this has to be there, this shouldn't have to be there. Okay, so, and that's what we say, right? When we ask any kind of prompt, when we ask any kind of prompt, basically, we expect it to give us the, regular prompt, regular answer, right? So we'll try to understand why this particular thing is, not regular, okay, moving down the road. But yeah, but if we just go to, there are a lot of stuff again, what is a regular language, and in regular language what kind of irregular expressions we can use. And there are different kind of you know expressions which we can use, such as, union, concatenation, and vectorizing, and all these you will understand, what is concatenation, what is a star product, and all. So you might have learned about the vector scalars and all that, multiplication and all that, right? So we'll pretty much learn all that moving down the road, right? So first, now let's see about the regular expressions. What are the regular expressions from the regular languages? Let's say, A and B are the languages, two languages, right? A and B, okay, are the two languages, right? Okay, so now when you're telling A union B, okay, that means, W, the words in W of A are W of B. I mean, like, the words of A or the words of B belongs to W, right? A union, this is nothing but the union of two different things. I mean, like, when you're, let's say, um, give me an Python code for so and so stuff, right? So when you ask that kind of a prompt, it assumes that yes, you are a developer who's a Python developer. You're seeking for this kind of a code, right? So it is the same thing. You don't have to really say that. You don't have to say that, okay, I'm a Python developer, can you please write me a Python code, right? You can just say, give me a Python code and so, right? Concatenation is nothing but, which is a dot product in another sense. I mean, like, we'll just put this dot, right? So let's say X and Y are the two products, where X belongs to A and Y belongs to B, which is nothing but AB, right? So when you have those scalars, vectors, and all that will really differ, right? And then when you have another thing in the regular expression, A star, that is equal to nothing but, x1 to x to the k, and each x1 xi belongs to a for k which is greater than 0. One thing which you have to note over here, the epsilon value which we have already looked at, right? It always belongs to a star no matter what. Okay, hope you got this right. So a star, right? So for example, let's say the examples over here, right? So for example, let a is equal to good, bad, right? And b is equal to girl and boy, right? Either way, right? Girl, boy. So when you're telling A union B, what it happens, this is something basic math which we have already learned, bad, girl, and boy, right? When you're saying concatenation, which is AB, right? Good girl and good boy, right? And bad girl and bad boy, right? And where a star, which is nothing but it's the epsilon value. No matter whatever that a star is, it always belongs to that epsilon value, right? Fine. So you'll get different kind of combination, good, bad, good, good, and good, bad, bad, good, and bad, 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 right? And it keeps going on. Good, bad. The goal over here is to show the finite automaton equivalent to the a regular expression, basically, right? The computing which you need to pretty much do that regular expression computing, which is pretty much equivalent to the algorithm. That's why it is very better to do that to the model, right? So yeah, this is the basic thing. Okay, when you're saying regular expression, where it is built from, basically, same the sigmoid member, okay, built from the sigmoid, and this is the member of, as you've seen, string, no string, empty string, and epsilon, which is atomic. Which can be seen, right, at some level. But when you're using union, all these regular expressions are built from here, from the sigma, and the operators such as union, star, and the concatenation, right? So for example, the 0 union 1 star, right? It gives sigma and gives all the strings, okay, all the strings of sigma. And with 1, right? And similarly, when you're telling sigma that concatenation, that consecutive things, right, which is nothing but all strings which contains 1, right, which is nothing but L of liquid. Okay, good. So in the next session, let's see what is the closure properties for the regular equation, as well as the properties for under the star, as well as under the union, things, right? So quick about today is, what we learned in this session is intro, an outline, mechanics, right, and expectations, right, and some finite automata and its formal definition. FA is nothing but finite automata and formal definition, regular languages, regular operations, and regular expressions. Okay, so we'll learn about the theorems, okay, which have to be under the closure properties and for that kind of an model, right? Cool. Thank you.